So hey guys, this video will be on CSE 236. This is a course I took at U of T, and it's called The Theory of Computation. I just gave its exam a couple of days ago. It was the worst final I've ever given. I think this will be the first final I've ever failed in university. But nonetheless, it was a very interesting course. I honestly enjoyed it for the most part, with all the coursework we had. The coursework was really good. And so I guess describe the kind of stuff I learned in this course. So this is like the theory part behind computation, Um, Theory of computation. And this is a math-based computer science proof. The first thing we learned in this course was, of course, the technique of simple induction. I'm sure many of you must have heard of this simple technique of proof, and it basically goes like, you start off with the base of simple induction is you're trying to prove a statement that you think is true over all natural numbers. So if it's true for, let's say you have a natural number n, if it's true for n, the principle of simple induction implies that it must be true for n plus 1 as well. So let's say if something is true for a particular natural number, let's say 3, it must be true for 4, for 5, for 6, and so on. And so the simple way to work with simple induction, or to prove things using simple induction, is you normally always have a base case first. So here you prove whatever you're starting off with. Let's say this is normally either n equals to 0 or 1, or maybe if you're starting off with, if the question is something with like n is greater than 8, then you start off with something like that, right? So you have a base case, you prove the base case, which is very simple. It's normally a plug into the formula kind of thing. And then you have the inductive step where, and this is like probably the most crazy thing about induction, is you assume that it's true for n. You assume it's true for n, and you use the assumption to prove that it's true for n plus 1. So this implies that will be true for n plus 1. Now this is probably the weirdest proof structure I've come across, because it's so counterintuitive, but that it is, I guess it must work for some reason. Okay, so that is simple induction. I would love to give examples, but I don't think I'll have enough time to go over all this, and there's a lot to cover, right? I'm just like kind of saying what I have done in this course. The second proof technique I learned was complete induction. So with complete induction, it's the same thing as simple induction, but instead of assuming n, you assume everything that came before n. So let's say you for some I in the natural number, you assume for all I such that it's greater than or equal to 0 but less than n, and then you use this assumption to show that it holds for, to show that n is true. So this is complete induction. Like most of the places I've used it is in, like, let's say the Fibonacci sequence, where you have a function that's recurring over the last few terms. Like it's based, the value of the function is based on the last few terms, and that's where you need to be able to assume that n minus 1 and n minus 2 are true for n to be true. So complete induction, very similar structure to simple induction, but except instead of assuming just n, you assume all every value of n that's come before. You assume every natural number before n. Okay, so I'm sure like these two are like something you must have all heard about, but this third induction proof is very it was very new to me, and this is called structural induction. So this is a type of induction which you do over strings. So the way structural induction works is you have a set, I think mostly likely a finite set, and you have some elements in this set, right? And the set has some structure to it, and you're trying to prove that if certain operations are followed, if the elements of this set follow certain operations, then then those elements will definitely be in the set. So let me give you an example. Let me just quickly. Yeah, okay. So normally it's the same kind of proof structure where you have a basis and inductive step, but let's say you have some x, y, and z. These are just some arbitrary strings, and these belong to, I think we normally call this set, it's denoted by this symbol, where this is equal to normally x, y, z. Or like it keeps going actually, my bad, right? And these are the singleton characters. So what we normally show is that if a single character is in the set, so our basis is to show that whatever property we're choosing works for the singleton character. So we can, because they're all like, it's arbitrary x, y, z, like it doesn't really matter what they're called. Just for simplicity, we can say let mu belong to this set epsilon. I don't think it's called epsilon. It might have a different word to this, but yeah. So we prove, or we don't even prove, we actually show, because this is not really proving. We show that mu holds, and by doing this we show that all of x, y, z holds. And then here's the crazy thing. Normally the kind of structure that we impose on the set is given to us in the question, but for now, for the sake of this example, I'm gonna say that, you know, let E1 and E2 be arbitrary elements of this set, okay? And just for the sake of example, E1 plus E2, if this is true, this is gonna imply E1 plus E2, E1 times E2, E1 minus E2, and E1 divided by E2. These are strings, and like, mind you that these things are not mathematical operations anymore. These are also strings. Like you can, they will have like quotes around these. All of these are strings, okay? And so you're not really dividing strings, you're not adding strings, you're not subtracting them. These are operations you're just doing. And you're saying that if you have E1 and E2 inside your set, then this entire string with the parenthesis will be in the set as well. This entire string will also be in the set. So, and your E1 and E2, you can probably see by now that this set can be extended infinitely. So if I have E1 and E2, so like my E1 and E2 could be like x could be E1 and y could be E2, then by the structure I'm imposing on this set, this implies that x plus y is in the set, x times y is in the set. And if x plus y is in the set, that means x plus y can also be E1 and E2 for the next induction. Like for the, it can keep on going. It's like this is what makes it an infinite set. So now this is E1, and like maybe this could be E2. And then if you do E1 E minus, you probably get x plus y. So that's E1 minus x times y. And you might notice I'm imposing these two extra brackets, because what I'm saying is every time you add an operation, you put a bracket around it. So this is E1 minus E2. This is basically what has happened over there. And so this is structural induction in its full flesh. What we would normally prove is, we say, you know, let an arbitrary symbol be in the set plus, minus, multiplication, division. And we prove that if E1 comma E2 belong to this set, then E1 at E2, so where at is any symbol from here, is also in the set. And so this is basically structural induction, where you're inducting over a set. This is an example. Obviously you can impose any kind of structure you want. It doesn't even have to be like operations. And the way, and like an example for a proof would be that, you know, or at least one we did in class was, let me just pull it up real quick so I don't really mess this up. But yeah, where is it? Okay, so for example, one of the questions we had was, we define new variables var e. So this is var e, and we say this is equal to the number of variables. So like x, y. So the number of these kind of variables, x number of variables number of variable instances in E. So that's var E, for example, and then operator of E could be the number of operators right? And we as we define predicates over here, I'm sure you must have known. So the way we prove it is we have a predicate P of n, and this is the thing we do induction over. So we also have a predicate over here, some P of n. So for in this case, we would say that var E equals to 1 plus operator E. So this is a predicate where I'm saying that the number of variables inside my E will always be equal to 1 plus the number of operators I'm using. And we can check it from the base case itself. So the base case here would be, okay, the number of variables over here, that's 1. Number of operators, 0. So it's going to be 1 equals to 1 plus 0, which is true, right? So we'll look for a base case. And like some extended examples, you can probably see two instances of variables and 1 operator. So that's 1 plus 1 plus 1, 2. It works out. Let's take this bigger case. 1, 2, 3, 4. 4 instances of variable. And how much? So this we have 1 and 2 and 3 operators. So this is 1 plus 3, which works out again. And so this is the structural induction proof technique we learned this semester. Okay, and I think the last flavor of induction or kind of induction we learned is called the well ordering principle. This is not really an induction as per se. Well, they argue it could be induction. It's more fundamental, or like it's just as fundamental as induction. But what it's saying is that if you have a set of natural numbers, and this is probably super intuitive to you guys, if you have a set of natural numbers, this set has a least element. And well, that's basically the principle. And we use it to, like, in some instances we can only proceed with the proof if we know that a set has a lowest element, and that's where we try to define the set over a natural number, or like index certain parts of the set over natural numbers, and so then we know that, okay, there will be a least element in this set, and that's the principle of well ordering. Kind of complicated to do proofs with this principle, but yeah, at least I find it. Okay, so this was basically, I think, the first part of our course. And I'll move on to the mid part of our course. Here is where I guess the real computer science stuff starts. We have regular expressions. So I'm just going to call them regexes. And regular expressions are super interesting as well. And in the sense that these are a set of strings containing only characters from some set. So with regexes, this is where the proof by structural induction and all comes very in handy. So let me just pull up my notes real quick. Yeah, so regexes is a subset of what we call formal languages. There's nothing formal about them except the fact that there's a structure that we impose on a set of strings, on a set of arbitrary strings. So probably some definitions that I should get out of the way is we have something that's called an alphabet, which is a finite non-empty set of symbols. So finite and non-empty. This is a set of symbols. So for example, we would have something like A, B, or 0, 1, -1. These are all finite and non-empty set of symbols. And usually they're denoted by the summation symbol. It's denoted by this. Then you have a string. A string is just a finite sequence of symbols over an alphabet. So you might notice that each element of an alphabet is a string as well. So you could have a string like A, but that's just it, right? Or you could have, oh sorry, no, it's a string is not a set, my bad. So A would just be a string, B would be a string, 0, 1, -1 would be a string, because these are the symbols over here. A, B, A, or A, B, B, A is the set of strings over A, B. And as you can see, it can be it's like infinite basically. You could pluck out any number of alphabets from here and just keep plugging them in, right? It'll be infinite. However, there could be so many random choices you make. You could go like an infinite number of A's in the beginning and then B's, or a mix of both, and there's no real order to it. And that's where the concept of languages come in. So basically, also a string is denoted by this symbol, which is just the sum but with a star. It's called the clean star, and it basically says any. Yeah, I mean, this is how it's denoted. So a language is a subset of is a subset of this. So it's a subset of strings for some alphabet given to us. And an example would be, let's say you have this alphabet. An example could possibly be A, 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 and it just keeps going, just an unlimited amount of A's going on for infinity. Or it could be a I don't know, I'm making this up completely. A, B, B, A, B, 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 where I'm just saying that, okay, the first element is A, but the rest is just any other element of the set. Right? So this is introduction to regular expressions. And the way we define regular expressions is that it's the smallest set is the smallest set over the alphabet such that the following conditions hold. If T and S are regular expressions, I don't know, can you guys even see this? Oh my god, I haven't even been checking. It's probably the shadow. Let me just like move one of the lights in the other direction. Give me one sec. Okay, it should be, sorry. It should be a lot better now, I guess. Sorry, I don't have the most fancy setups. It's just lights, like lamps. Okay, this is much better. So if T and S are regular expressions over the alphabet, over this, like I said, this is called the alphabet. It represents the alphabet. Then we also have that T plus S belongs to the reg X, belongs to reg X. T S belongs, and this is just denoting the regular the set of regular expressions, and so is T clean star. So if T and S, so like let's say if A and B are regular expressions, then so is A plus B, AB, and A star. What this means is basically if you have A and then you do B, this is basically just set union. So you get A, B, you get A comma B. And if you do AB, then you just get AB. And the clean start just means 0 or more repetitions of T. So 0 or more repetitions of A or B, whichever you choose. So the regular expressions are defined inductively, but I should also say before this, there is another like small base case kind of stuff that you need to check. So like let me call this point 0, where the symbol, I think you guys can still see, yeah. So this is the empty set, epsilon, which denotes the, so this is the null set, this is nothing. This is the empty string, and this is the base string, I guess. And if they are in the regular expressions, so this normally form the basis of our regular expressions, and then we can prove T plus S, TS, and T star are in regular expressions. Then here comes the second part about it. So these are regular expressions. Now we have this thing called languages. Languages are just representation of regular expressions in set form, I guess. So regular expressions are something like 0 star, 1, 0, plus 1 0 1 concatenated with 0. Like, this is some random stuff I just wrote, and this is how you denote a regular expression. This is a regular expression that says that, okay, whatever it is, it must end with a 0, because whatever you're bringing over here, you're concatenating a 0 to it, and it must start off with either this or this. So it's gonna be either 1 0 1 0, or it could start off with this. So it could have 0 or more zeros. So 0 or more zeros, that's what the clean star means, followed by 1 0, and so that's where this comes from, and then it must end with a 0 as well. So it's an either or, right? So this or this followed by this. So that's a regular expression. Languages are a set. So let me define languages as well. The languages so languages are described by the regular expression structurally. So let me write down quickly the basis is that if R is regex, defined by the structure that I've given over here, then we can define the language over the regular expression as So I'm sure you must know, you're familiar with set builder notation. So what we're saying, and recall that these were the bases over here, where we had, the null set, epsilon, and x. So the null set just defines no set. It's not a set. It's not even, you can't even call it the empty set. I think I might be confused. Oh yeah, it is the empty set, but epsilon is the empty string. So there is no string over there. It's like you pass in nothing, and that's what epsilon is. And x is the first element of the string, not of the string, but x is the base case of our alphabet, basically. And so this is the basis, and now we have the inductive step, which goes something like, if we have R, which is a regular expression over here, then so L of s plus t is equal to L of s union L of t. L of s t, you might be, I'm being very careful with my brackets, because the way how we define structurally is that you must have your brackets encapsulating your operator and your strings. So that's why I'm having it. LST equals to L S L T, and L of s star is basically L of s star. And the languages, they define a set. So a regular expression can look like this, but let's say you want the language, so 0 plus 1. So this is a regular expression, 0 plus 1, and this is the language is just 0 or 1. It's a set. And this is the same thing as L of 0 union L of 1, which is 0 union 1, which is again 0 comma 1. Right? So that's what I'm saying in our inductive step. You have L of s plus t, so this is 1s, this is a t. I'm saying that this is 0 comma 1, and how am I claiming that? Because by our inductive step, this can be written as L of 0 union L of 1, and which is basically in set notation 0 union 1, the set containing these two elements, which is 0 1, which is basic set builder stuff, right? And then if you have L of 0 plus 1 clean star, this is basically the set of all binary strings over 0 1. So it'll be any set of binary strings over 0 1. There's no way I'm writing an infinite number of strings here. But yeah, that is the gist of formal languages and regular expressions. Good. Okay, we're going kind of slow, I feel. I mean, yeah, I don't know how much faster I can explain this stuff. The next stuff we have is machines in CS. So DFSA and NFSA. So this is basically saying what this stands for is the deterministic finite state automata and the non-deterministic finite state automata. So what is a finite state automata? Well, I'm saying in a finite state automata is that it's basically used to describe languages. Um, I don't really know how to explain it, but let's see. So a DFSA is described by a quintuple. So this is described by, and this is probably the most fun kind of stuff I did in this course because it was basically all drawings described by a quintuple. I'm pretty sure I butchered that spelling up, but let's say I have, it's a quintuple that um, that has elements, that has these elements, and I'll really quickly tell you what these all say. So this is the set of states of the machine. Set of states of the machine. This is the alphabet over which the machine is running. This is the initial state of the machine. Initial state. This is the final state. Final form. And this is a transition function. This function kind of determines how you move from one state to another. So let me get a good example. Okay, so let's say you want to make a machine that describes the language L such that L is the language of binary strings, language of binary strings with an odd number of zeros. Okay, so the way we describe this machine is we'll say, okay, let's have two states, a machine with an even number of zeros, which I call E. Sorry, not a machine, my bad. This entire thing is the machine, but this is a state that the machine would be in if it has an even number of zeros. And if it has an odd number of zeros, the machine would be in this state. So this entire thing that I'm going to draw is the machine. And we have to use this, since the machine is described by this quintuple, my Q would be E and O, where E is the state if the machine has even number of zeros, O is the state if the machine has an odd number of zeros. My final state, because I want it to be, I want the machine to accept strings which has an odd number of zeros. That's the point of the machine. I want it to accept, if I pass it in a binary string, I want it to only give me back the strings which had an odd number of zeros. So my final state would be, I'm not sure if this is a set or not, but yeah, this is my final state. And to denote the final state, we normally put another circle around it. The alphabet that I will be using is, for this to make any sense, I should have defined this in the beginning. It's 0, 1. So the obviously you can represent the binary strings using just 0 and 1, and that is the alphabet that the machine accepts as well. And my transition function would be, so let's say I come in with I start off with my start. I'll obviously have to start off here because you remember the epsilon I was telling you about? That's the empty string, and vacuously the empty string has an even number of zeros because it has none, and 0 is an even number. So that's why I start off at even here. And let's say I get a 0. If I get a 0, I go to this, the machine moves me over here. The machine moves me from the even state to the odd state. Let's say I get another 0. Then what does that mean? It means, well, I'm back in the even state. Okay, that's good. But what if in either case I get a 1? What if when I start off, the string I immediately get is 1 something, right? Doesn't have to start off with a 0. And if that's the case, well, it's a self loop. I stay in the state if it's a 1. I don't want to go anywhere. If it's just a string of 1s, like an arbitrary long string of 1s, then the machine won't accept it and I just remain in that state. What if I get a 1 here? Same thing. I just stay there. So I could have 0, 1, 1, 1, and I'll just be there until I get a 0 back when I move back there. So that's the machine. This is deterministic. You know, for each string, for each value in the alphabet, what you're doing. And the function here would be represented as, so we have, well, this is complicated, but basically I don't know how, I forgot how the exact structure is, but it's basically that, you know, if I'm at an even state and if I get a 0, well, I'm going to the odd state. If I'm in an even state and if I get 1, well, I stay in the even state. If I'm in the odd state and I get a 0, I go to the even state, and if I'm in the odd state and I get a 1, I go to the even state. So that's basically the structure. Now we have a non-deterministic FSA. It's basically the same thing as a DFSA, but now instead of just 1 0 going there, let's say we have another state, right? Some arbitrary other state, let's just call it a mixture of both. So over here, you know, if you get a 0, you're going there. But now I can just say that, okay, a 0 could also go here, and then a 1. So what this is telling me is that this is very poor, but this is a very poor example because I didn't really think this through. But this machine will now accept if you get a 0 and a 1, 0. So can you guys see the flow? So let's say I come off in the start here. One way of getting accepted is if I just get an even number of zeros, like 0, come back here, 0, come back here, 0, come back here. But now I've created this other path where I can also be accepted if I have any number of 1s, then I get a 0, then I get a 1, and then I have anything else I do over here. So basically this is telling me I will accept any binary string that has 0, 1 as a substring of that binary string. But this is non-deterministic because you don't know if you get a 0, if you're going to this new state or if you're going to this new state. And that's where the non-determinism comes in. And there is a technique which we can use to make this into a deterministic machine, and that is basically it's called the subset construction, where I define new states. So let's say E with a 0 goes to E0 and E with a 0 goes to 0 O, then I define a new state, and well, E would go to this with a 0. I hope I got that right, but yeah, it's very long. I don't really want to get to the nitty-gritty of that. But the important thing with the connection between machines and languages is that they're all equivalent. A DFSA is equivalent to a regular expression, which is equivalent to the NFSA, because these two can be represented. You can represent an NFSA as a DFSA always, and a DFSA is just a representation of a regular expression. So that was the key takeaway, and I'm sure like now you must know why structural induction is super important to prove stuffs with these kind of things. Okay, the next thing we learned was recursive time complexity. So for those of you who do any theory with computer science, we are normally very concerned with how long the algorithm takes to run, whether it's efficient or not. And we have these notions of big O, big omega, and big theta. This was like a prerequisite, so we did this in the previous course that I did last year. And so basically big O tells me that a function is bounded above by a function. So let's say I have some arbitrary function f, and if this belongs to the big O of g, what I'm saying is, well, this function for any value after a certain point will always, so g will always dominate f. So let's say you have a graph, and if this is my function f, g could be like something like that, you know, like after a certain value on the number line in the x direction, my value for g will always be greater than f. So that's what it means to be in big omega. So what I'm doing is, this is what it means to be in big O. What I'm doing is I'm bounding the function f from above. Big omega is similar, as you can guess, but it's from below now. If that's my f, then my g could be something like that. And then I say f is in omega of g, and big theta is basically a sandwich. If f belongs to theta of g, then f belongs to big O of g, and f belongs to big omega of g. And you might be wondering, that's crazy, but I left out some stuff. So remember how I said it's going to be after a certain value x? you can multiply f and g, or you can multiply f with any factor as well. Any constant factor you can multiply with it, and it should hold true for most cases. So you could have, yeah, I don't really know how to draw it, but let's say if like these are like g's, I guess, multiplied by a different factor. So maybe it might go like that, and then your f is just sandwiched in between. So that's the concept of big O and big theta. And the place, so basically we did all this with recursion and merge sort and the concept of divide and conquer algorithms. Well, I wasn't really always the best with it, but that's something I learned as well. And lastly, what we did was correctness. This was pretty interesting. When you write an algorithm, how do you know your algorithm is correct? And what do we mean by being correct? Like, you obviously want to be able to test your like without actually running your algorithm, you would want to know beforehand itself if your algorithm would work, right? And for an algorithm to work, I guess one important place to start off would be, well, let's see if the algorithm terminates. Like, it shouldn't be, if I give it a set of inputs, I don't think in any situation I would want my algorithm to run forever. Like, maybe it might be running forever to get a result, but I want it to end at some point. I want that result, right? And so there's a way we can check for termination. How do I do this simply? Okay, so with correctness, what we're proving is that we have a loop invariant. Well, this is a very small case, sub case, I'm pretty sure, but this is the context in which we learned it in. Loop invariant and termination. This is what we want to prove. By the way, we did correctness with recursive algorithms and iterative algorithms. And you guys must know these are like kind of similar, except they accomplish the same thing, but like using different methods. So if we talk about iterativeness, if you have an iterative loop, if you have a loop, then we define a loop invariant, which is basically a statement that is true after the end of each loop, and we prove that. And we also have a termination, and the way we prove that a loop terminates is we associate a sequence of decreasing natural numbers with the loop iteration. So let's say if you're in the ith iteration of the loop, you want to define a sequence of natural numbers that is decreasing first of all. So if it's decreasing, you know that and if it's a sequence of natural numbers, well, by the principle of well ordering, it has a least element. Maybe that's 0, maybe that's 1, whatever it is. And if the sequence of natural numbers I define has a least element, and if that sequence is somehow correlated to the number of iterations, then the loop terminates, right? That's just, it's not, I shouldn't say it's logic, but if the sequence terminates to some finite value, then the loop must also terminate, is their argument. And so that is basically that's how we prove termination of a loop. We also did pumping lemma, but I never really studied the pumping lemma. Kind of sad, but yeah, it's all very complex actually. Like, there's no way I'm able to gonna go through all of this. Yeah, this final I wrote a few days ago just got over. By the way, I'm in my second year obviously, and because of COVID, all my exams got cancelled, which was so surprising. There's this wave of Omicron going, and U of T, University of Toronto, just drops a bombshell that, well, all your exams are cancelled. And this email comes on the 15th of December, and I had 2 exams on the 14th of December, which I'd already written, one being quantum physics and the other being this one, CSC 236. And holy shit, did I bomb this. This will probably be the first final I'll fail, like maybe 30% if I'm being optimistic. No, I'm joking. 40% if I'm being optimistic. But yeah, so I was kind of salty that they didn't send that email a bit sooner, but at the same time I'm happy because I really wanted to write that quantum physics final, because I wanted to really know, I really wanted to test my knowledge of quantum physics and how much I do understand. And so I had so the other 2 exams I wrote. On 16th December, I had a software design final, which is called CSE 207, on which I shall also make a video. And on the 18th, I also had my physics 254, which is classical mechanics exam. This course and these course, they were like, okay, not that bad, but yeah, so those are the two in-person exams I missed, but it was a huge bombshell. Like I really didn't have any emotion. It was like such a mixed bag of emotions. It felt like IB all over again. Literally the exact same emotions, the exact same reaction I had. But yeah, that's pretty much it. I don't really know how well this turned out, but thank you for listening. If you guys did listen, this is basically everything I learned in CSE 236. Obviously, there's more. These are just the main overarching topics. Proving things using these principles is a bit trickier, which is probably why I screwed up big time in the final. But yeah, see you guys in my next video.